Okay, in this section, we will learn some basic operations of complex numbers. So here are two complex numbers, and then we know that this constant -2 will be called the real part, and this 5 will be called the imaginary part. And we also know that this I square is equal to -1. So let's see what kind of operations we can do. So we can certainly add and subtract one from another. That will be easy. But let's look at something slightly more kind of challenging. So z square. So z square is z times itself. So -2 plus 5i. So there are two ways you can do this. First is you can still think of it as square, and then you can use the square of sum of formula, right? So it's the first term square, second term square, minus 2ab, right? So then this is 4, this is 25, but then be careful, I square is -1, so it's negative. And then this is positive 4 times 5, so 20i. And then this is -21 plus 20i. So another thing we can do is divide. So for example, if we want to divide z by w, -2 plus 5i, 3 minus 4i. Okay, so the key thing to do for division is to multiply both the top and bottom by the conjugate of the bottom. So let's kind of extend this. So I want to, so the idea is we want to get rid of the I in the denominator. So to do that, we will multiply by its conjugate. So that would be 3 plus 4i. So in order to keep this quantity like unchanged, if you multiply something in the denominator, you need to multiply the same thing on top. So 3 plus 4i. So then this stay unchanged, it's still z over w. So then let's look at the denominator first. So you can think of it as, a minus b times like a plus b, right? And then it will be equal to a squared minus b squared. So 3 squared minus 4i squared. And then on top, I guess the only thing you can do is like foiling. So this is -6, -8i, plus 15i. So these two multiply together. Be careful, it's 20, but it's negative because you have I squared, so -20. And then let's clean this a little. So the bottom will be 9, and then again, be careful, I squared is -1. So with that negative, it will be positive 4. And you see it, the imaginary, the I will be gone. So then you just have constant in the denominator. And on top you have, so the real part is -26. The imaginary is 7i. So then this is -26 plus 7i over 13. Okay, so that's division. Another thing is taking kind of, it looks like the absolute value, but it's called the modulus of a complex number. So the way to get that is to take the square root of the real part square plus the imaginary part square, right? Without the I. Because we want to, so geometrically, if you write it, if you think of the -2 and 5, the 2 and 5 as being the kind of the lengths of a kind of sides of a right triangle, then this modulus is just the length of this side. So that's square root of 4 plus 25, which is square root of 29. Okay, so that's called the modulus of a complex number. So another thing we can do is we can plot a complex number in the complex plane. So for example, if I want to plot z equals negative square root of 3 minus I, how do I plot that in the imaginary in the complex plane? So this is gonna be the real part of z, which we call it maybe x. This will be the imaginary part of z, which we tend to just call it the y-axis. So then so this is like your x, and this coefficient is like your y. So you're just plotting negative square root of 3 comma negative 1. So that's gonna be maybe like roughly here, right? So if this is negative 1, this is negative square root of 3, then this point corresponds to your z. Right? And then if we want to find the modulus and the argument, right? So modulus, we said one way to find it is algebraically, it's kind of the square root of sum of square. So we know that's going to be 2. And then, like I said, geometrically, it's kind of the length between this point and the origin. So, right, so this is a right triangle. So this is 1, this is square root of 3. So this length is 2. So you can see it from the picture why this is 2. So another thing is called the argument of a complex number. So that just means kind of what kind of angle this complex number kind of correspond to. And one thing to know that is this argument, it's not unique, right? So you can see if you just add or subtract 2 pi, like multiples of 2 pi, if you it just means on the picture, just rotate by like a full circle or 360 degree. So that doesn't kind of change the angle, how it looks. It does change the value, but it's still gonna be on this line. So that's why this arg z, it's not unique. But then we just need to maybe find one value of it. So we can either find it this way or this way. So let's do it this way, because it's kind of the direction I'm like kind of used to. So if I call this kind of the angle theta, what would that be? Because this is a special right triangle, we know if the sides are 1 to like square root of 3 and 2, and then we know maybe the first thing that comes to my mind is this is pi over 6. So then that's so that's gonna be pi over 6, which means this whole theta will be pi plus this pi over 6. That's gonna be 7 pi over 6. So that can be our argument, even though you can add the multiples of 2 pi or subtract 2 pi from it. So that's another kind of, so this arg can be considered as an operation you can do on the z. So other kind of operations you can do, just as practice. So we talked about this. If you have a z that's, let's say -1 plus 4i, we know this is notation is called a complex conjugate. So you're just changing this sign, right? Changing the sign for the imaginary part. So that becomes -4i. So that's easy. And then we can also maybe multiply these two together. So what is z times z bar? -1 plus 4i times its conjugate. So I'm used to think of this as, I call this -1a, call this 4i b, and then it's just plus minus, right? So I can use the formula a squared minus b squared. So it's -1 squared minus 4i squared, which is 1 minus, I like to put a parenthesis to kind of, so that, it's safer to deal with the negative sign that will be coming out from I squared. So it's I squared is -1, so it's -16. So that's 17. So find your own way to kind of avoid making the mistake. So it's very easy to miss a sign here. So I'm used to putting an extra parenthesis to deal with that. But find your own way that makes you feel comfortable doing this. Yeah. So that's kind of the basic operations we can do. Another thing to note is that this z times z bar, it's gonna be the modulus square. And so this, if you think about it, when we do the when we compute the modulus, we're kind of taking a square, without the I, like b squared, this 4 square, and take the square root. So then if you square it, you kind of get rid of the square root. So this is kind of an identity, and we can verify that. So what is z? So if we were to just compute modulus of z, we have, it's the sum of squares of real part, imaginary part. So -1 and 4, which is square root of 17, right? And then if you square this, you get back this 17, which is z times z bar. So you can, I guess the conclusion is that you can think of this as a identity or a formula that might come handy. Okay, so the next video we're gonna talk about Euler's formula. So that's a really interesting formula that relates a lot of like seemingly random things together in one formula. Okay.